Hi everyone, welcome. My name is Vikash Yadav. I'm a data scientist at Royal Bank of Canada. I work as part of Joint Security Operations Center, also known as JSOC. We are a group of 6 data scientists. We are not cybersecurity experts, but we work closely with threat hunters, penetration testers, and SME from different line of businesses from RBC. To enhance overall security posture of RBC. The topic of today's talk is detecting DGA using deep learning, which is area of machine learning, and how can we enhance or improve the performance of these DGA detection using separate correcting embedding model. So I'm going to cover all of these terms as part of my presentation. So if you don't know, don't worry about it. We'll cover all of these terms in detail as we go through the presentation. So I've divided the presentation in 4 sections. In the first section, we are going to look at the problem, what we are trying to solve. Next section, we look at some of the already available approach to tackle this problem, both the traditional as well as machine learning based approach. Then one of the most popular machine learning approach to tackle this problem is recurrent neural network. And we are going to talk in depth about that technique, how it works, and what are the advantages or disadvantages of that technique. And in the last section, we are going to discuss some of the enhancement or improvement that we are making so that to improve the accuracy on detecting unknown DGAs. So with that, let's start with the first section. So the malwares are everywhere. Even in the most secure organization, you can always find some malware that are trying to exfiltrate the user information to an outside malicious actor. Detecting these malware requires different approach for different stages of that malware. Each approach has a different advantages or disadvantage. A typical life cycle of a malware starts with initial compromise, and the initial compromise could happen through phishing email, or it could be user going to some sketchy website, or through some known vulnerability in the system. Once a malware gets a foothold on a host, it then scans for the kind of security control in place in the organization to get more idea whether there are firewalls, whether there are proxy servers that are trying to block the communication. So once it captures all those details about the environment, then it initiates a connection to a command and control server. A command and control server is a centralized hub, a rendezvous point that's controlled by the hacker. It's the point where the malware is going to send the data that it stole from the user. Once a successful connection is established with the command and control server, the malware can then start receiving the instruction. Those instructions could be the patch of code to be more effective in the environment, or it could be to move to a higher privilege system, laterally move to a higher privilege system so that the information that can be sent out is more useful. We are focusing our attention on the connection to command and control server. Once malware is in the environment, it's going to reach out to C2 server. And this communication we want to detect as soon as possible. In early days of malware, the IP address or domain name of that C2 server would be hard-coded. So it will always reach out to the same server. But modern malwares are much smarter than that. Instead of using a hard-coded IP address, they use what we call domain generation algorithm, or DGAs. DGAs are a small program that takes a seed and or time-dependent element and generates a lot of domain. The malware then uses these domains to make connection to C2 server. And as you can see, here is a Python script of a DGA algorithm that takes year, month, and date as input, and based on that, it's going to generate 16 DGA domains. The malware is then going to use these domains to make a connection to C2 server. And these domains would change every day. So it's not like you can block them one day and then the malware is stopped. These domains would change every day and you have to keep blocking them every day. Some of the techniques that are available to tackle this problem involves both traditional and machine learning. The traditional approach is to get a hands on the binary of DGA. Once you have the binary of DGA, you can reverse engineer the code to identify the underlying DGA. And once you have the DGA code, you can in advance generate the domains that the DGA is going to generate in coming days and proactively block those domains. Or you can also register these domains yourself and try to take over the control from the hacker and sinkhole the C2 communication from the malware to these C2 servers. These traditional techniques are reactive in nature. You have to get your hands on a malware binary. Once you have the binary, it takes a lot of time to reverse engineer and get to the part where you have a DGA in your hand. And this is not a very scalable approach because it takes a lot of time to reverse engineer the binary and get the DGA code. With the advance of machine learning and natural language processing, there are a lot of new ways to tackle this problem. I've categorized these detection technique in 3 different parts. The first one is NXDOMAIN DNS request-based detection that looks at the DNS traffic in the network. If a host is making large number of DNS requests to non-registered domain, then it could be a potential DGA communication to C2 server. The second type of technique are ML approach using handcrafted feature. These technique requires explicit feature engineering. The third type of technique is RNN-based detection, and this is one of the most popular one because it tackles the shortcoming or limitation of the first 2. I'm going to give a brief introduction of the first 2 and what are the limitations. NXDOMAIN DNS request-based detection. So as I mentioned, DGA is a small program that generates a large number of these domains, and the hacker only registers a selected few of those domains. So the malware has to query the DNS to identify which one of those generated domains are actually registered. And once it finds a domain that's registered, it's going to use that domain to start communication with C2 server. So if in DNS traffic we can find a client that's making a large number of requests to unregistered domain, then it could be a potential sign of DGA malware infection, because a normal user would make 1 or 2 queries to unregistered domain because of some typo or some other issues, but nobody would make 20 or 30 DNS requests to unregistered domain. This is a very good technique to detect DGA, but this is still a reactive approach. You have to constantly aggregate the DNS traffic, and as soon as the number of these unregistered domain requests reaches a certain threshold, then you are going to flag that client. But you have to wait a certain period to aggregate the data to know that a client is making large number of requests to these unregistered domains. The second type of machine learning approach to detect DGA communication is based on handcrafted feature. This requires explicit feature engineering, and these features could be entropy of the domain, length of the domain, looking at the ratio of vowel to consonant, the periodicity of the request between the host and C2 server, how popular is that domain, and what's the total number of bytes sent between the host and the server. This works well. It tries to identify the abnormal traffic in proxy logs. So for each client, we have a baseline behavior, and whenever a client is making certain communication to an outside C2 server, that's very far apart from his normal routine, his normal behavior, this ML technique is going to flag that because it could be related to a malware C2 communication. One of the limitations of this technique is that it takes a lot of time and effort to select the right feature to be able to differentiate between the normal human communication versus a DGA communication. That's why RNN are so popular, because it addresses the shortcoming of the first two techniques. It doesn't require any explicit feature engineering. It accepts the domain name as input, and it separates those domain in either it's a good domain or it's a DGA domain. And through the training process, this technique is going to learn all the relevant feature. I don't have to specify whether the entropy is important, whether the length of domain is important. Through the training process, the model is going to learn which features are important to differentiate between a normal human generated domain versus a DGA. This is a proactive detection technique. As soon as somebody is making a request to a domain, you can use your model to detect whether it's a DGA domain or a normal domain. And you can straight away block that communication if it's a DGA. These are easy to build and easy to deploy and doesn't require any maintenance. If your algorithm is becoming outdated, you can simply add new samples, new DGA sample, and retrain your model and deploy it back. It's very easy to deploy these models. It's highly scalable, and this is highly accurate in detecting these DGAs. We're going to go in depth this technique, what are the different components of this technique, how these pieces fit together, and what are the detection accuracies that we can accept from this technique. So this is an architecture of a RNN model. There are 4 components. The input is the domain name, which first goes through an embedding layer that learns a vector representation, and I'm going to talk about that in the next slide. Then passes through an RNN LSTM layer, and the final output is a probability. What's the probability of the input domain being a DGA? If it's high enough, you can block that DGA from communicating to C2 server. Machine learning model such as RNN requires a huge amount of data to train. You need lots of input to be able to learn the correct parameter, to learn the correct features, to differentiate between the two categories, good domain versus DGA domain. So for that, we are using Alexa and Cisco top million most popular domain. These are the domains that normal users frequently go to, such as Google, YouTube, Facebook.com. And for the DGA domain, we are using 1.1 million unique domains that are collected from NetLab 360. And as you can look, some of the sample for DGA, these looks very different from benign or user-generated domain. So we're going to use this data set to train our model. And we are going to use 60% of this data to train, to learn the right feature, to train our model. And then remaining 40% we are going to use to validate how good our model is performing in detecting these DGA, and how good will it perform in future. The input, which is the domain name, is then passed through an embedding layer. So the machine learning model requires a fixed size numeric input, but our domains are sequence of character. So we need to pre-process this input in a machine learning readable format. So the first step is to convert these character sequences to integer sequence. Here each character is mapped to a unique integer. And since the domains are of varying length, we also need to pre-process it by padding additional zeros so that each domain is now of a fixed size. This input sequence is now of a fixed size which is acceptable to a machine learning model. However, this integer sequence is one-dimensional input. It doesn't have any contextual information. A character represented by a digit 5 versus a character represented by a digit 6 doesn't mean that those are close to one another because there is a difference of 1 unit, versus a character that's represented 5 by a character represented by 20. Here, although it looks like the distance is large, 15, but it doesn't mean that those are far apart from each other. So this encoding is not suitable. It doesn't have contextual information, which characters should be combined together, which characters occurs frequently together in our input data. That's what the embedding layer is going to learn through the training process. The embedding layer takes this integer sequence as an input and then converts this to a higher dimensional, 8-dimensional input space. You can think of each character as a point in this input 8-dimensional input space. And through our training process, the embedding layer is going to learn which characters occur together and hence should be close to each other in this 8-dimensional input space, versus which characters are corresponding to DGA and should be far apart in this input dimension space. We don't have to encode that information. The model is going to learn that through the training process. This input is then passed to the next hidden layer, which is recurrent neural network. Recurrent neural network are special kind of neural network. A traditional neural network takes an input and then makes a prediction. For example, a handwritten digit system. It takes an handwritten digit image as input, and based on that image, it's going to make prediction whether that image is a 7 or 8 or whatever number it is. Here, the prediction only depends on the input that we are passing to the model. But for the tasks which have sequential input, such as a sentence, I grew up in France, I speak fluent, and then the model has to predict the next word. Here, the input is sequential in nature. And predicting the correct output depends not only prior word, but it depends a sequence of word that occurs much prior in the sequence. So here, predicting the next word French is dependent on the keyword France that occurs much prior in the sequence. And because of the recurrent structure of these RNNs, the model is able to capture this long-term dependency in the sequence to be able to make the correct prediction. One of the special structure that is used in RNN is called LSTM, or long short-term memory cells. These memory cells are kind of a complex nonlinear function, and these are designed specifically to mimic the human brain. We as human, when we read a sentence, when we read some passage, as we go through the line by line, we remember certain keywords that are important and memorize these words in our memory. And then we perform 3 kind of operation. One, we constantly update our memory with new keywords. As we read further and further in the sequence, if we encounter a new keyword that's relevant to the context that we are reading, it's going to update that keyword in memory and it's going to retain it, so that later when somebody asks us a question based on the keywords that are retained in our memory, we can make the correct answer. The second type of operation that our human brain does is to filter out the information that's no longer relevant. Perhaps we moved from one context, from one topic to another. Now the information or the keyword stored on our mind is no longer relevant. And hence, the mind starts deleting that information. It starts filtering out those keywords because those are no longer relevant for the context that we are reading. And the third operation is answering the question based on what's stored in the memory. So if somebody asks, I speak fluent, which language, and I have few keywords stored in my memory, one of them is France, then the model filters out based on the current input what's the most important keyword that's stored in the memory, and based on that, it's gonna answer the correct word French. So RNN mimics this human behavior through this complex nonlinear structure. It has 4 parts. So the core part is called cell memory. It's similar to our human memory, and it retains all the keywords that are relevant and observed as part of the sequence. And then it has 3 gated structure to constantly keep updating this memory. First one is the forget gate. Based on the current input, whatever information is no longer needed, it's gonna delete that from the cell memory because it's irrelevant now. Maybe we moved from one paragraph to another paragraph, and the information that was available in the first paragraph is no longer needed. So it will delete that from the cell memory. The second is update part. Based on the input, if the input is interesting, it's going to add that to cell memory so that it can retain and memorize that information for the later use. And if the information is not relevant, it's a common keyword, then it will just ignore that input and keep the cell memory constant. And the last one is output, which combined input with the cell memory to predict the correct output word, which in our case was French. So LSTM and RNNs are really good at sequence prediction problem, where we have a long sequence and at the end of the sequence we want to make a prediction. So RNN and LSTM captures this long-term dependency that's ideal for sequence prediction task. And our domain name, which is a sequence of character, can be LSTM can sort of memorize which sequence of character are for benign domains or human generated domains versus which character sequences are for bad or DGA domains. Coming back to the unified architecture, as I explained all the different sections, the input is the domain name. We pre-process this input to one-dimensional integer sequence because the machine learning model only accepts fixed size integer sequences. The embedding layer is going to convert it to a more meaningful input space. It then passes through an LSTM layer, which is going to remember which sequence of characters are for normal good domain versus which character of sequences are for DGA bad domains. And the output is a number between 0 and 1, which represents the probability of the input domain being DGA. Higher the number, the more probable that domain is a DGA. So we train this model on our data. We use 60% of our input data for training the model, and then we validate the accuracy of this model on the test data, which is 40%. We want to see how our model will perform in future when it receives new data. And what we found is that for benign, which are good domains, human generated domains, the model is able to detect 99% of the time, 99.4% of the time, it's correctly able to identify good domain. And for malicious DGA domains, it's able to identify 98.5% of the time. So this is very high accuracy in detecting DGA. Also the F-score, which is a number between 0 and 1, and generally used for model accuracy where the two classes are imbalanced. Here the benign domains are more in number as compared to malicious domains. F-score gives a measure of the accuracy of model when the two classes are not equal. And since 1 is the highest number, our model is very close to 1. So it has very good accuracy in detecting these DGA. But these are for the non-DGA. We use 60% of the data in training our model, and then we asked, can this model now detect rest 40% of the data? So this accuracy is in detecting non-DGA. We wanted to know how our model would perform in future. Say our model is running in production and somebody creates a new DGA, and we didn't use those samples in training our model. So it's the first time that our model is encountering those domains. Would our model be able to detect these new domains? And what we found is that these are the 3 DGA families. And what we found that for the DGA family, which has samples very similar to what the model saw in the training data, it gives very high accuracy. For example, for China DGA type, the model gave 99.6% detection accuracy, because the samples are very similar to what we pass in our training process of the model. But for the Shifu family, which is a DGA which is very different from what the model has seen in the training data, it's much more closer to a benign good domain, because the length of the domain is very small. So our model didn't do very well on these type of DGAs. So we thought, what could be the possible reason that the model is not able to perform equally well on the new DGAs, something that it has never seen before. And this is very important for model to be deployed to production, because in production we want our model to constantly detect these new DGA even if we didn't use them for our training. And some of the limitation for this model is possibly because of overfitting. And the second reason is that the embedding representation, which maps characters to a more meaningful 8-dimensional space, is trained on it learns that representation through training data. So it's only what we pass to our model that it's gonna convert to that input dimension, 8-dimensional input space. This is somehow limiting in nature. We want, as a human being, even if I see these samples, I can easily separate them out. So why can't the model do it? And that's because we as human, when we read through the text, we have a certain information or certain embedding captured in our mind. And that embedding of a natural English language is different from what model learned through the training. So we propose a change to this model. We want to change the embedding part of this model, because that's very limiting. We want to add some flexibility. So what we propose is to have a separate character embedding model that's going to be trained on normal English text instead of the input domains. And through that training process, it's going to learn which sequence of characters usually occur in English language, natural English language. It's going to have that contextual information about English language encoded as part of embedding representation. And we are going to use this general representation of English language to then convert our domains to a vector space. So here is our embedding model. And the purpose of this model is just to learn the embedding representation. Here, as an input, we are passing the newspaper articles from popular US newspaper. That's very much representative of normal human English language. And the output would be, given a sequence of n characters, can the model correctly predict the next character in the sequence? And through this training process, the model is going to learn the embedding representation that's very much comparable to our human mind of English language. We're going to use that embedding representation learned on natural English language, and we are going to plug that back in the unified architecture. So this architecture is very exactly same as unified model. The only part that's changed is the embedding representation. In unified architecture, we trained both the bidirectional LSTM layer as well as the embedding layer as part of one unified architecture. Here, we are just going to train the LSTM layer, and we are going to keep the embedding layer fixed. We then validated this new trained model on the same data. So this was the accuracy of the unified model that we trained earlier. We wanted to know if these changes would break the model or would it still work with these new changes. And what we found is that yes, our model works equally well even if we don't train the embedding representation as part of unified architecture. For benign domains, the model is 99% accuracy. And for malicious domain, it has slightly higher accuracy, 99.8%. The F-score, which is a measure of a model's accuracy, is still very high. It's very close to the one we saw for the unified architecture. So this shows that this change didn't break our result for the existing non-DGA types. So it works equally well. Where our unified model was not so good was in detecting new unknown DGAs, something that was not part of training process, something that it has never seen before. And the accuracy for Shifu DGA types was really low. But with our changes, our separate character embedding model has 39% higher accuracy as compared to unified model. So we have a unified model that works well on the known DGA, but doesn't work equally well on the unknown, which is really important. And with our changes, the separate embedding model not only works well on the known DGA, it also works really well on unknown DGA, which is very important for the model to be deployed to production. To summarize, LSTM are highly effective in detecting DGAs. As we saw, the model gives 99% accuracy. It's able to detect DGA with very high accuracy for non-DGA. And with our proposed changes, it improves the accuracy in detecting the unknown DGAs as well. And the last, RNN approach is a proactive. You don't have to wait a certain period of time to aggregate the traffic like NXDOMAIN based DNS detection, and it also doesn't require a huge effort to train. You just pass the input data and all the relevant feature would be learned by model. So this is a proactive, very highly effective technique to detect DGAs. With that, any questions?
Thank you, Vikash. Any questions from the room? No questions? So I really loved your talk, and it was nice to hear you talk about how you improved the detection of unknown DGAs by using more the natural language as humans do see it. And yeah, I'm happy you could take Hugo's place, and I hope you all enjoyed this talk as well. So in about 26 minutes, there will be a launch here in front of the free area for the conference attendees, I believe so. I hope you enjoyed it, and I hope to see you in the next talk after lunch.
Thanks, everyone. Thanks for joining.
Oh, there's one more message. Hugo, that was originally scheduled.
Yeah, hi, my name is Ali, and there is a question with respect to DGA, what you were showing. Okay, so it will generate random DGA domains. So just wanted to ask, like, won't it be easy for any analyst to detect such type of suspicious traffic, because the domain is not a normal domain. So if someone has a look into the network, it will definitely come to know that this is something not a normal domain. So it shouldn't be like generated based on something very common. Because the domains which has been generated by the DJ, it would be something which is not a normal and a common domains, and it will be easy for people to look around for something is wrong in the network.
Yeah, as a human, we are naturally very good at detecting these random sequence. If we look at a sequence of character, we can easily detect whether that sequence makes sense or not. But in a large organization where on daily basis user makes say 100,000 requests on a given day, it's very hard for an analyst to go through all those requests and manually search for the ones that are DGA, right? It's very time consuming to go through 100,000, and that's for a moderate organization. For an organization like RBC, which has 80,000 employees, on a daily basis, we have close to 80 million requests, and doing it manually, and an analyst going through that entire traffic is impossible. So that's why we need something that's not manual, something that's automatically detecting random sequences.
Okay, thank you.
Yes.
Hi, this is Ashwin here. The entire method or process that you mentioned about the detecting of DGAs, is it something already available in a product, or is it something that you have developed inline or in-house of the Royal Bank of Canada?
So different vendors, proxy servers, different DNS server, they have their own technique, which is not known to RBC. Some use traditional techniques only. Some use some version of machine learning techniques, the RNN ones. What we are proposing here is a way we use the embedding layer. So this is a very common approach in other type of network, like using ImageNet to identify, say, two different kind of image, dog or cat. So for training those kind of model, for those kind of tasks, we don't train our model from scratch. We use a pre-trained model like ImageNet and then add some additional layers and then train those additional layers only. We don't train the entire network. Okay. But this is something that's missing from the RNN-based techniques that's commonly proposed by the researcher. They train the entire network, both the embedding and the LSTM layer, as part of one unified architecture. We don't want to do that. We want to add some flexibility to model. We want to have a character embedding model that's representative of a normal English language, and we're going to plug that pre-trained weights in our model, and then just train the hidden part, the LSTM part of the model, to separate the normal character sequences versus random character sequence.
Thank you.
Any more questions?
First,
I saw
one
a finger in front.
Thank you. My name is Ibrahima. Is the LSTM released actually in order to be used, for example, having the list of the DNS requests in order to check which one are probably DGAs?
So LSTM is basically a non-linear function. It's available as part of Keras or TensorFlow or whichever deep learning tool that you use. You just simply add an additional layer and say that I want to use LSTM in this hidden layer. So yes, you can definitely add LSTMs.
Any more questions from the room? I might have one question for you. I've come across some malware that generates domain names based on titles of most read articles of a specific website. Have you come across these, and how do you think, or how does your model perform against that, or how do you think it would perform against that?
So those type of malwares or DGA malware that uses English word are called dictionary DGAs, and are different from the ones that just uses the characters and a random combination of those characters. The dictionary DGAs picks any two random dictionary words and combine together. Those dictionary words, if you read, those won't have any meaning, right? But since the model that we propose here looks at the character sequence, this won't be as effective in detecting those dictionary DGAs, because the character sequence is still very similar to natural English language. The difference is that now instead of combining random characters, it's now combining random words. And one of the ways to tackle this kind of DGAs would be, instead of embedding each character to a vector space, we would be embedding each word. So here, say there are two words, word 1 and word 2. These are two dictionary words that are combined to form the dictionary DGA. Instead of embedding each character in this domain, we are now embedding each word. And Google has this word-to-vec representation, which maps each word in the English dictionary to a vector representation. And that vector representation, the words that frequently occur together, such as king and queen, are very relevant to each other and frequently occur in the same context, would be close to each other in that vector space, versus the word that doesn't make any sense are generally, which doesn't have any relationship with each other and are usually used in these dictionary DGA, would be very far apart in that input space. So through the word embedding, we can then separate out these dictionary DGA. The character embedding is not as effective in detecting these dictionary DGA, and have to use the word embedding.
Thank you. Any more questions? We still have some time, I think, so. Okay, that's it. Thank you, Vikash.
Thank you. Thank you, everyone.